Hello all, myself Venu Bhatt from MNCF. Today we are here to talk about atomic force microscope AFM. We have two atomic force microscopes at MNCF, that is in Center for Nanoscience and Engineering, Bangalore. So what is atomic force microscope? Not many might know. Microscopy is a very familiar topic, but AFM might not be such a familiar topic. Let's go and see what that is. Principle of working of a atomic force microscope. There is a sharp nanometer size probe that is attached to the end of a cantilever that interacts with the surface. So it is raster scanned across the surface in a very near field above the surface, and because of the tip interaction with the surface, we are able to get some images. And how do we get these images is by monitoring the movement of the tip. That is done by the software with the help of a computer. If you look at the family of scanning probe microscopy, we also call this AFM in general as a scanning probe microscope. There are other instruments which are very similar to them. They are scanning tunneling microscopes, then scanning force microscope, that is also other name of atomic force microscope. Then we can have many other specialized techniques and setups. Let us look at the history of how atomic force microscope came into existence. It all started with the invention of scanning tunneling microscope, that is STM. It was done by Binnig, Rohrer and Gerber in 1982, for which they were also awarded a Nobel Prize in 1986. When we have a new technique, these new techniques come with limitations. One such limitation with STM was the sample needed to be conductive or semi-conducting. So they had to invent something other than this, which could actually do some imaging on non-conducting samples. So as a result, in 1986, another group of people which also had Binnig and Gerber, so the new person was Quaid, they invented atomic force microscope. So this atomic force microscope had capability of doing measurements on non-conducting samples as well. If you look at the atomic force microscope, this is how the schematic looks. It has a main scanner head which can scan over a XY stage. So this is where we would keep our samples. And this is a controller which talks to both the computer and also the scanner head over here. So this controller has all the lock-in amplifiers, feedback controller, and also high voltage amplification factors here. This is how the schematic looks. Again, coming back to atomic force microscopy principle. So how does it do it? So there are different ranges of or regimes of interaction above the surface. If you take a tip which is attached to the cantilever very close to the sample, how would it interact with the surface? So there are different ranges of forces which we call as long range forces and short range forces. If you look at them, there are electrostatic forces in air, magneto-electrostatic forces, double layer electrostatic forces. These all come in long range forces. They are around 100 nanometers in range above the surface. But when we come to just the atomic force microscopy technique, these are all done in short range forces. So van der Waals forces, surface induced solvent ordering, hydrogen bonding forces. Then there are contact, the mode that is called contact mode, which is done at even closer range, that is around 0.1 nanometers. So atomic force microscopy is done in this short range. So how does it work? Atomic force microscope. If you look at any sample, if this is the surface, this is how the surface is, then the tip that is attached to the end of a cantilever, that would trace the surface somewhat like this, as it shows in this in the screen. It would trace the surface like this, depending on where you are doing it. Are you doing it in the repulsive regime, or are you doing it in the van der Waals regime? So repulsive regime is where the contact mode is done, and van der Waals forces, which are also called attractive forces, that is where this tapping mode or non-contact mode is done. And this, when it is doing it, it is rastered across the surface, above the surface, somewhat like this. And how the, while rastering it, how the tracking is done is by pointing a laser on the cantilever. This cantilever will have a reflective surface, and in turn, when the laser falls on that cantilever, the reflective part of the cantilever, it will go to a detector. So whatever reference point we have initially will keep changing when this cantilever, the tip, interacts with the surface. So somewhat like this, as represented on the screen here. So as the cantilever goes around this surface here, it moves away from the reference. So this spot which was in the center of this photo detector, this is a photo detector, it moves away. So that is kept, that is kept a track of and shown by the computer, or computer keeps getting the data from this photo detector. By doing that, it is able to generate images. So whatever image we get from this, it's called computer generated image, or a pseudo scale image, pseudo color image. And how it does is, by doing the line by line scan, this is the representation of line by line scan of cantilever going to and fro above the surface. And by doing that, it is able to generate height profiles of each lines, something like this, for everything. And this is all put together by the computer, and with the help of the software, it is able to give us a pseudo scale image. And every color here will have a meaning, and this meaning is taken from the scale bar given over here. So what can we relate this atomic force microscope to? From that we see in our daily life, right? So if you have to give an example, this is one such very good example. Everyone knows about this. This is a Braille script, and we do not use it, but blind people use it, right? How do they use it? So they feel across the surface, right, over the surface, and skin being a very good sensor, it is able to see what is on the surface, and it is able to give send signal to the brain, and brain generates an image which is very similar to the atomic force microscope generation of image. So this is a blind tip that is represented here. There are different models of AFM that are possible. Normally, generally, the AFM comes with the tube scanner. We can see it here, where either the XY stage is sitting on the tube scanner, or the Z and XY, all three are sitting on the tube scanner. And they have their own issues, problems. Then there is another model where it is called a decoupled model, where XY scanner is different and the Z scanner is different. So this moves independently of this. But what we need to understand is, it's always a relative motion of the tip with respect to the surface of the sample. And with these tube scanners, they have the issues that I just told you about. That is called image distortion that can happen when you are doing large area scans. Decoupled XY scanner apparently gives the most accurate AFM images. Cantilevers and tip probes, how does it look? So we will be looking at this in a demo anyway, but this generally is the very general design which goes on any atomic force microscope, be it Bruker, be it Park System, be it Oxford. These are all the very standard design. This is called a chip or a base, which has the cantilever. This cantilever is this, and this tip over here, which we cannot see here, is this. So these tips can have pyramidal shape, these can have tetrahedral shapes, or even conical shapes. Or you can even imagine a carbon nanotube sitting at the end of the cantilever, which can also become a tip. So this is the more zoomed in image over here. As you can see, the specifications, these are some example specifications that are shown to you. Material of this cantilever usually is made from silicon or silicon nitride. This is what you get commercially. And typical height is around 3 to 20 microns, and also radius of this cantilevers, radius of this tip or the probe ranges from 2 to 10 nanometers. You can also have higher radius tips. Depending on what application you are doing, you will have to change these cantilevers, or you have to use different cantilevers. Again, coming back to what can we use it for, this is an example of step height imaging over here. You can see there is a difference in contrast depicting there is a change in the height in these steps over here. So you can also use it for roughness measurement and other things, height distributions. So here what we have shown to you is, after imaging, using the analysis software, we have put two lines, different lines over here. These lines are shown here. So this is the top view, this is the side view, this is the cross-sectional view. So you can see there is a difference in height. So we can use, there are many analysis softwares that are available. Using these softwares, you can put these cursors accordingly and see what is the height difference. Similarly, if you concentrate on delta x instead of delta y, you can also see what is the radius of a particular particle, or even diameter of a particular particle, or width of a trench, things like that. This is another example where we are showing the top view, that is the 2D image, and also the most beautiful thing about AFM is that it is able to give us the 3D representation of the surface of the sample. Now, this is one such example where there is some crystal sample. We have used some crystal sample. Also, we can use this AFM to do many other non-conducting surfaces. Some examples are proteins and some DNA. So this is a image of DNA, super called DNA. You can also have this AFM doing imaging of DNA origami, right? And also this is another example of rat trachea. And using this, you can see what is the size of DNA. It's around this much, 280 nanometers, 240 nanometers. This is what has been recorded. There can be some deviations from what is expected, but this is expected because the lateral resolution of anything that you measure in AFM is dependent on how sharp the tip is. So with the tip going bad, the resolution also goes bad. Other examples of usage of atomic force microscopy technique is to do what is called magnetic force microscope. There are many other modes that you can do. This is one such example where we have shown you magnetic force microscopy. So this is normal topography image that is similar to the, when you say topography image, that's a height image, right? While doing the height image in the same area, what is the magnetic, what are the magnetic domains that is sitting just beneath it, if there are any. So this is how it looks in the same area. So this doesn't interfere with the topography, and this comes out to us in the form of a magnetic domain image like this. Here, this has nothing to do with the height image. So we can have this atomic force microscope doing many other things, like atomic force microscope in air is the most general thing that we do. Similarly, you can do AFM in fluid, then you can do it in vacuum in a controlled environment, and also in a controlled environment where we can choose a particular gas to be inserted in the system. This slide tells you about what are the other things that you can do in a single machine of atomic force microscope. So these are some standard imaging techniques which we spoke about: tapping mode, contact mode, non-contact mode. You can also do magnetic force microscopy, lateral force microscopy. Then there are other chemical properties measurement, then the electric piezo properties measurement, electrical properties measurement. You can do a lot of other things, but all these things will differ from machine to machine. Whether a particular machine is capable of doing it or not will depend on whether that company provides that particular module. And if that particular module is there, then whether have you bought it for your system. Depending on that, you can do all these modes. Coming to sample preparation, AFM is surface sensitive, and so the features shouldn't move. The surface features shouldn't move. So we have to have a fixed substrate, and the sample that is there on the substrate, that also shouldn't move. So the general method of preparation is like this. The surfaces can be mica, silicon, graphite, glass. There are many other possibilities here, but the thing to be understood is this: it should be fixed on a solid substrate. It should be a sturdy substrate. Then you can have depositions on the surface. You can do it using many techniques: evaporation, normal deposition, spin coating, sol gel technique, rubbing, everything. But thing to be taken care of is, if you are doing AFM in air, that is the most general technique. This sample, whatever we prepare, should be completely dry. There shouldn't be any moisture on it, or else what can happen is we can have this problem of capillary effect, which can affect the imaging, and we will not get any good images. Talking about the specifications of AFM, I am talking to you about what we have in MNCF here. We can get vertical resolution as good as 0.1 to 0.3 nanometers, but 0.1 is a very ideal situation where you don't have any noise coming into picture, but then that's very difficult. At the same time, lateral resolution is also very good, 2 to 10 nanometers, but again, 2 nanometers is very difficult, because it also again depends on how sharp the tip is. But 10 nanometers is very easily achievable if you have prepared the sample so nicely, like if the sample is very neat and clean. Then coming to scan size, what is the maximum scan size, scan area that you can measure? We have two atomic force microscopes here. One is Bruker and another is Park system. In Bruker, we can scan a maximum area of 90 by 90 microns and height Z range of around 15 microns. And at the same time, in Park system, we can have a scan area of 100 by 100 microns. And again, sorry, this is not mm, so there's a mistake here. So this is 15 microns again. The Z height is 15 microns. And sample size, coming to sample size, what we can accommodate is its variable area. You can have a very small sample, 1 mm by 1 mm sample also, but the thing is, again, coming back to the previous slide where I was telling, the sample needs to be sturdy. It should not move. So if you can do that, we can have variable areas. And 50 millimeter thick is the maximum thickness. That's around that's the sample thickness that you can accommodate in these two machines. So thank you. That was about AFM. This is just a simple presentation that I showed you. Now what we will do is we'll look at a demo, which I suppose will give you a better idea of how AFM works. So now we are going to load a cantilever to the tip holder. So this is a tip holder over here. After loading the cantilever on this tip holder, we will load this tip holder to the scanner head. So how we load the cantilever to the tip holder is this. This is a sharp tweezer, what we use, and we pick up a cantilever like this. But what we are handling with the tweezer is not a cantilever directly. It's the base that was shown in the presentation. So the base contains the cantilever and the cantilever contains the probe. So it is held like this, then loaded onto the tip holder like this. So the tip has been loaded onto the tip holder, and this tip holder after the loading needs to go onto this scanner head. This scanner head is the most crucial part of the machine because it has a piezo scanner inside, and this piezo scanner can get damaged very easily with any small impact on it. So one should be very careful while handling it. So what we'll right now do is load this tip holder to the scanner head with good caution, very carefully. So how we do it is, there is a screw here to unscrew it so that it loosens up. Then we will take it up and then load it. It's taken out like this very carefully. It's called a dovetail fixture. Now, as you can see here, there are 4 pins. To these 4 pins, there is a correct alignment. We match this holder and press it. It's a press fixing fixture. Once that is done, you get a feel in your fingers that it is fixed. You put it back again very carefully. We cannot just drop it down. Once it has gone into its position, base position, we tighten this screw again. After this, we are ready to do further scans by switching on the software, and for that we will look at the screen. These are the 2 controllers we have. This is called the NS5 controller, and this is called the stage controller. And right now, as you can see, there are no LEDs on over here. That tells us that the controller is off. So before we switch on the software, which can control the AFM here, we need to make sure that these controllers are on. So the controller switch, the power switch is right behind it. It's a very simple power switch, what you find in any machines. So we have to switch it on. On switching on the controller from behind, you can see the LEDs glowing. Once these LEDs come into life, then we can go to the software. So we have switched on the controllers. Now we can go ahead and switch on the software. Software is here. You can see Nanoscope 9.4. When we switch it on, so this is a window that pops up when you when we switch on the software. And as you can see, there are different modes that you can do: scan, assist, tapping mode, contact mode, electrical and magnetic, mechanical properties. Many modes that you can do. And some of the modes might not be possible or can be possible depending on whether that module is there with us or not. So I will be right now showing you a tapping mode experiment. So I'll select tapping mode, and in tapping mode we will be selecting the standard method and say load experiment. Never be in a hurry. If there is a buffering showing, let it run on its own time. Otherwise, if you click any other things, there are chances that the system will hang. Because the controller was off and it was restarted right now, so it is asking us a initialization, and whenever this initialization pops up in the screen, we say yes. Once the initialization is done, once the stage has stopped, this pop-up will come, will ask you whether to return to the original XY stage position. We can always say no. We have already loaded the tip holder onto the scanner head. Now the remaining main step is to align the laser on the cantilever. So to do that, first step is to tell the machine what is the cantilever we have loaded. So we are loading first step is to tell the machine what is the tip we are loading. That is, we are loading right now TESPA V2. We say yes, save. Second is the main step, that is the alignment of the laser. To do that, when we click on this move to alignment station and say yes, the stage will automatically move to a known position where this part is called alignment station, will come directly underneath the tip cantilever. where we will be able to see the cantilever position and also the laser spot. Using that, we can align the laser onto the cantilever. As you can see on the screen, this is a cantilever. This is the base or the chip which we held with the tweezer, right? Now the idea is to get the laser onto the cantilever. What will happen when we put the laser on the cantilever is, this detector will show certain voltage output. Right now you can see it's almost zero, negligible. Let's see what happens when we put the laser on the cantilever. So as you can see on the screen, the laser is not visible over there. So to bring the laser onto the cantilever, there are two knobs here. So this is for X movement of the knob, this is for the Y movement of the knob on the screen. So initially what we do is, we rotate the cantilever, we rotate this laser knob in anti-clockwise movement. Again remember, this should be done in counterclockwise movement, so that the laser comes out to the left and it is come out in the screen, we can see it now. And once the laser is in front of us, there is no confusion. You can move this Y knob again adjust the position of the laser onto the cantilever such that we get a good voltage output on the photodetector. And this laser spot should be at the end of the cantilever and not at the base of the cantilever. It should be somewhere here. Once that is done, we move to the other two knobs here on the side. These are to adjust the spot on the detector. So rotate it such that the spot moves to the center. Once the spot has moved to the center, next step would be to get our focus on the actual cantilever position. This image on the screen is not actually the cantilever position. This is the image of the cantilever on the alignment station. What we do is, we click on this return from alignment station. What it will do is take the camera focus onto the actual cantilever position. So on clicking on this return from alignment station, when you get this pop-up, would you like to move back to the sample analysis position? You can always say no. And when we do that, as you can see, the focus has returned to the actual position of the cantilever. If it goes a little out of focus, again you have this focus control here. You can click on that. Once this is adjusted, you can zoom in and get this crosswire onto the tip position. So that is done by just clicking once on the cantilever. After this step, we go to the tuning of the cantilever because we are doing in tapping mode. So go to manual tune, check here the start and end frequency. It should be the start frequency should be below the actual resonant frequency of the cantilever, and end frequency should be above it, so that when it tries to tune it, it should be able to sweep those frequencies. And on clicking on auto tune here, we will be able to see the peak over here on the screen, and this is an automated step, and it will do it on its own. We should be ideally getting a peak like this, very nice peak like this. Right? Once you get this, we click on zero phase, which is the adjustment of this. This is the derivative curve of this curve. Click on that and say exit. Next, we will move to the navigation, that is by clicking here. Once we click on that, we will be able to move the XY stage, so that we will, once we load the sample on the stage, we can move the sample under the sample that I am showing you here is a calibration grid sample, specification of which is 3 microns pitch and around 44 nanometers in depth. This sample is taken out and put on the stage here, where in the center there is a small hole, and it is a vacuum check, vacuum hold, and to hold the sample, we switch on the vacuum switch here. Using the software, we will move the stage up. First, we will move the stage up like this, so that the Z scanner comes up and gives enough space for the stage to move in. Then this is for navigation of an X and Y. We can adjust this speeds over here and then move the stage. Now for more finer refined positioning or movement of the cantilever over the stage sample, we can use this joystick as well, or we can always use this software that's always there. We can also use this joystick so that we get the Z stage a little more closer towards the surface. Z stage more closer to the surface, what will happen is we will be able to see the optical image over here. This is the optical window of the sample. Once the sample has come into focus, we stop the movement of the Z, and the idea is to go to a clean area to avoid any dust particle, dirt on the sample, so that we get a clean area for scanning. So you can navigate again using this. So always remember to adjust these speeds, or you can double click to an area where you want to go and scan. So once we have the area, then we go to what is called check parameters. Here are the parameters that you can set, like sizes, scan size, and other parameters which we need to adjust to get a good image. So first thing we do is tell the computer how much is the area we want to scan. So as I told you in presentation, the maximum area that we can scan is around 90 by 90 microns, but we won't be doing that here because the sample pitch is around 3 microns. So we will try to get 3 or 4 boxes in a single row. So let me give around 15 micron area initially. 15, U is microns, NM is nanometers. Aspect ratio 1 tells us it's a square. Then we can also opt to give X and Y offset once we start a scan. If you don't like that area, you can move it in -X, +X, -Y, and +Y. Then you can always change the scan angle also. That is all after starting a scan. Then scan rate. What scan rate means is it is the speed of the rastering of the cantilever over the surface. You can also control that. So usually we keep it around 0.7. It is up to the user depending on how the scan is coming, how good or bad the scan is coming. We have to be open to adjusting it. Once these are done, we can opt to engage, that is to tell the tip to approach on the sample surface. When we approach on the surface, that is by clicking on engage, what will happen is the cantilever will be pushed towards the surface automatically by the algorithm that is there in the software. So I will click on engage, and we won't be able to see this movement, Z movement, if you look at the scan ahead also, because that's a very subtle movement. But you will be able to see it on the screen here. So the cantilever gets focused, and slowly the cantilever gets pushed towards the surface. And ideally, while doing these measurements, it's always better to close this hood. Like this. And you can also opt to lock it over here. But just by closing this much, we will reduce a lot of acoustic noise that can interfere with our measurements. So right now we can see that the cantilever is in focus and also the sample is coming to focus. That is to tell the sample and cantilever, they are very close to each other. And once the engage is stopped, that is the approach is finished, the cantilever will start moving. So this is where we control the amplitude set point. The cantilever is approach, cantilever is moving to and fro. Now as you can see, the tip is not interacting very well with the sample over here. You cannot see anything. So then what we do is, we reduce what is called the set point here, amplitude set point. So as you can see, the value is around 260, 66. So from that, when we start reducing it, we will be able to see certain change here. Now how much you change here depends on how well the scan is coming here, or the trace retrace is matching together. And once the trace retrace starts completely matching, we can stop reducing the amplitude set point, and also increase the integral gain so that this matches very well. So this is a pretty good setting that we have done right now. Once the parameters are set, once you are happy with the parameters that you have set, you can give a fresh scan like this, frame down or frame up. If I click on frame down, it will start from top and go to the bottom. Frame up, it will start from here and go to the top. So we'll give a frame down. And here on this part of the screen, you will be able to see what is the amount of time that is left for the whole image to be, this particular image to be captured. For this to be saved, you have to create a folder. So to create a folder, you go here, select capture directory, and then create a folder where you want it, and you can save these images. Name of the sample is given here. You can give any name, or if you have a particular name for your sample, you can name it. Right now I am going to name it in a simple fashion. I am just going to tell you, call it 1. Once you do that, we click on capture. What it will do is, at the end of this image, it will capture that particular image. And you can always see here at this part of the screen, if the capture is on here like this, it will tell you that at the end of this scan, it will capture it. In case the capture says capture next, then it will not save it at the end of this image. You will have to wait for its turn again. Now you can see the image is already completed, and it has started going in the other direction because this is in scan continue. So once we are done with the scanning, what we do is we click on withdraw. When we click on withdraw, what will happen is this cantilever will come to a safe position. That is, it will be lifted to a safe position by the software. That is around 1 mm. So we click on withdraw. Then click on navigate. Here, if you want to go to another area for a scan, what you do is simple navigation. You either by using these arrow marks or double clicking wherever new place you want to go to. Then do the same thing. If you want to scan, go click on engage. And if it is on the same sample, you might not have to change any parameters. The same parameters will work. Let's say you want to change to another sample itself, then what you'll have to do is you'll have to bring the stage out and then load the next sample. So to do that, or even to finish the experiment, what you do is click on sample load position. When I click on sample load position, what will happen is the scanner head will automatically come up and the stage, XY stage, will be brought out towards us automatically. That is also an automatic movement. So click on sample load position, you can see it has raised up, and also this stage is coming out automatically. Once you do that, once this comes out, switch off the vacuum. This vacuum again, coming back to vacuum again, it is only the check vacuum. Once you switch it off, remove the sample carefully and place it in your sample box. Then again we need to remove this, remove the holder. That also needs to be done very carefully. Slowly. All the way down, and when you put it down all the way in a controlled fashion, finally to look at, you need to look at this part where there is a sketch pen mark. As you can see, this should be seen to us completely properly. Then tighten this screw. So like this we handle the AFM very carefully, and what is expected of any user is to handle the instrument in a very cautious way, so that it doesn't damage the scanner head part. Once that is done, this tip holder is taken back to the loading station over there, and the cantilever is removed and put in its cantilever's box. This removing the tip or the cantilever from this is similar to how we loaded initially. Hold the tip holder, press the clamp over here and push it back. Now remove it and place it in the box. Once the image is captured, it is shown here. Here, this is the captured image. This can be opened in the analysis software by double clicking it. As you can see, there are quite a few other images that are captured, but this is the present image that we captured, which initially looks like this, but any AFM image that is captured usually needs a correction. So the main correction that's needed is called flattening. So we do the flattening. Different softwares will have different ways of doing it. Flattening is a way to remove the exaggeration that comes in the picture due to the features on the surface. We do this for the entire region, all the surface features. Here we see that it is no thresholding, flattening thresholding direction, then say execute. So the final image looks something like this. This is the 2D image, but the beauty of AFM, as I already told you, is with the 3D imaging part, 3D representation. So that is shown to you by this. So we can change the angle of it like this. So this gives us a pretty good idea how the surface is, and that can be used for our help. Then to measure anything on the surface, we go to this section. We can draw a line like this. Once we do that, we can move these cursors to any point you want. So first thing, if you want to see the step height, you can see what is the step height over here. Similarly, you can also measure the width of anything, or if you want to see what is the width of a particle, the diameter of a particle, you will have to look at the horizontal distance here. It will give you the distance between these two walls. So this is one very simple example that we have shown of a grid sample. Likewise, you can do many other samples to see the roughness factors and other things. To see roughness factor, we have another option called roughness over here. So here, this is not the right image to show that, but then in image roughness table over here, results table, for roughness factors, you need to look at image RQ. RQ stands for RMS roughness, that is root mean square roughness, and RA stands for arithmetic mean, that is average. So if the image is right, you can look at all those data points. So this is in simple about AFM that we saw in the presentation. So this was about AFM. I showed you a simple presentation and also the demo. Hopefully this will be helpful for you to do your get your training done, and also to understand how the AFM works. Thank you.